Hello student, welcome back to very fresh lecture series on Fourier transform. So from today onward, we are going to upload a complete lecture series from M3 subject in our channel. It's completely based on Fourier transformation. It's not our first lecture, so if you want to see similar videos, I already uploaded plenty of the videos for another units. You may go and check in my playlist. So in our today's video, I'm gonna explain to you all Fourier transformation, okay, with some of the examples plus some formulas, okay. Now see that for finding the Fourier transformation, we need some important formulas. They have their derivations also, okay. So the proof it is also there, but we are not going for the proof as the formulas are important here for solving the question, okay. After Fourier transformation, so we have two types for Fourier transformation. Which one of it is the Fourier sine transformation or Fourier cosine, okay, Fourier cosine transformation. So these two transformation we are going to learn. First of all, we'll see first here what is the Fourier transformation, okay. Yes, so to explain Fourier transformation, you need to first of all be the familiar with some of the concept, okay. So what is the even function, what is the odd function, plus some of the standard formulas, okay, that we needed here. So let's get started our today's lecture. First of all, I'm going to explain to you all some basic concept with the formulas, and then we go for the Fourier transformation. So first of all, we see what is the even function and odd function. Then we go for the even function for the Fourier sine, Fourier cosine, odd function for the Fourier sine, Fourier cosine transformation, okay. Yes, so let me explain what is the even function first, okay. I'm going to explain here even function. Even function. So even function means, what is the meaning of basically even function? Whenever we have negative sign under that function, okay, whenever we have negative sign under that function which gives us the positive value, okay, that means whenever we have f of minus x, okay, f of minus x, whenever we have f of minus x which gives us the positive f of x, okay, that means it observes negative sign, so we consider it as the Fourier even Fourier transformation, okay. Just consider for it right now even function, okay, even Fourier even cosine, even sine Fourier transformation, I will explain it later, okay. Even function means whenever we have f of minus x which gives us the f of x, okay. So for example, let me explain with one of the example. So if I consider example here f of x as a x square, I consider f of x as a x square here, okay. Now see that whenever we have f of minus x as a f of x, okay, so see f of minus x can be written as minus x square, okay. So we can see that f of minus of x square means negative term square, it always gives us the value positive. So we write f of minus x minus of x square, that means we write x square. So we can see that here, okay, we can see that here f of x which is equal to f of minus x, f of x is x square, f of minus is x square, okay. Whenever we have f of x which is equal to f of minus x, f of x which is equal to f of minus x, then we write is the even function, okay. Let me explain with another function now. I explained here with the algebraic function, okay. So instead of that we replace here trigonometric function. Now see here even function for trigonometric identities, okay. So we know that cos and sec, these are the two trigonometric function, they are even, okay. So how it is even, let me explain even function now, okay. So if I consider f of x as a cos x, okay, f of x as a cos x, so what is the f of minus x? F of minus x cos of minus x, okay, cos of minus x. And as we know that cos of minus theta and sec of minus theta, these are the even function, okay. So it observes the negative sign inside, so we write f of minus x as a cos of x here, okay. So now see that f of x is a cos x and f of minus x also cos x, so we write f of x and f of minus x both are equal here, f of x which is equal to f of minus x. So in this case we write cos x is the even function, cos x is the even function, okay. Now let me explain odd function now. After odd function we go for some of the results, okay. Odd function. what is mean by odd function. Okay, odd function means whenever we have f of minus x, it gives us f minus of f of x. Okay, that means it extract negative sign out of the function. Okay, so f of minus of x, which is equal to minus of f of x. Okay, now let me explain with one of the example. We go for one of the algebraic and then a trigonometric. Okay, so it will be concept will be crystal clear, very much clear for us. Okay, yes, example, f of x I consider here as a x cube. Okay, you can consider any x, but don't go for the even power. Okay, so it observe negative sign. So f of x I consider is a minus x, f of x as a x cube. Okay, so what is the f of minus x then? Minus of x to the power 3. Okay, we know that negative to the power 3 always minus x cube. Okay, f of minus x is a minus x cube. Now see that f of x, which is equal to f of minus of f of x cube. Okay, now see that multiply negative sign to the two side. Okay, so minus of f of minus x, which is equal to x cube. I taken that negative sign here. Okay, so x cube, which is equal to f of x, and x cube, which is equal to minus f of x. So we write f of x, which is equal to minus of f of x. Okay, so now see that, so this one is the absorption of the value. Okay, so f of x, which is equal to minus of f of x, we get it here. Okay, then we write this one is our odd function, or instead of that you can take as a trigonometric function. Okay, so if I consider f of x, as a sin x. Okay, consider f of x as a sin x. So what is the f of minus x? My sine of minus x, or sine of minus theta. We know that f of minus of sine theta. So f of minus x is equal to minus sine theta. So f of x, which is equal to minus of f of x. Okay, so whenever we have f of minus x is equal to minus of f of x. Okay, f of minus x, which is equal to minus of f of x, then we write given function. Now see that f of minus x is the minus sine theta, and minus of f of x multiply minus sine here. So minus sine x, which is equal to minus of f of x. So we say that this and these two terms give us a equal value. That means sine x, x cube, these are the odd function. Okay, that means this function extract negative sign outside, and remaining function absorb negative signs. That's why they are even function. That's why this one are odd function. Okay, yes, I hope you all have understood this one. Yes, this is just even odd function we need to know. Okay, after this we go for some of the standard format. Okay, that we know that De Moivre's theorem. Okay, e raised to I theta, we write it is from the complex analysis. Okay, a raised to I theta, which is a cos theta plus I sin theta. Okay, a raised to I theta can be written as cos theta plus I sin theta. Okay, or if it is a e raised to I times n theta. Okay, we write cos n theta plus I sin n theta. Okay, yes, this one is our De Moivre's theorem, which is important here for our further part of the calculations in our Fourier series. Okay, yes, Fourier transformation. So we use some another results. Okay, bipart rule for integration of u into v. Okay, dx. So I know that you all are familiar with the bipart rule for integration. So we take u into integration of v minus integration of a derivative of u into integration of v dx. Okay, yes, this one is the bipart rule. We use one more bipart rule for finding the integration. Okay, for finding the integration. So we write integration of u into v dx. Okay, yes, so we take u outside, integration of v minus u dash into integration of v, double integration of v, minus plus minus in u double dash. Okay, u double dash into triple integration of v plus so on. Okay, now see that just what I am doing here, I am taking u as it is outside, integration of v inside, plus this one is a minus, this one is a plus, this one is a minus. Okay, this one is a minus, this one is a plus, and this one is the minus. Okay, these are the integration. Let me write it again, integration of u into v dx. So we write u into integration of v dx minus take the differentiation of that term, which is u dash, into integration of integration, take the integration of this step again, v dx plus minus again plus u double dash into triple integration of v dx minus, and so on. Okay, So this one is the integration of u into v. I written here. Okay. Yes, I hope you all have understood how can we write this integration of a by-part rule. Okay, these are the formulas used here, useful for our further calculations. Yes, now one more result that we needed here. Okay, so integration of these are the important result for our Fourier transformation. Okay, because we are going to solve so many differentiation, integration. Okay, for that these formulas are needed. So integration of 0 to infinity sine x upon x, okay, dx. Integration of 0 to infinity sine x upon x dx, we write it as a pi by 2 and minus pi by 2. Okay, so when we write pi by 2, whenever we have that x, okay. Yes, now what we have, sine x upon x. Now it is not only the x, we write ax. Okay, sine x, maybe it is constant possible as, okay, sine x upon x dx, so which has the value pi by 2 or minus pi by 2. But when pi by 2 possible, when that a is positive, a is positive. Okay, when a is positive, and when we have a which is negative, we write minus pi by 2. Okay, a is negative. Okay, these results are very much important here for our further calculations. So next result, okay, what we have next result, whenever we have combination, okay, it's like a product rule under integral, okay, e raised to ax. Okay, whenever we have product rule under integration e raised to ax sine bx dx, okay, and whenever we have integration e raised to ax cos bx dx, okay, this type of the integral if we come across. Okay, so how we solve? Now see that e raised to x we take as it is, we take e raised to x as it is, e raised to x as it is. Now see carefully how I am going to explain these results. Okay, yes, first e raised to x keep as it is. Okay, this one e raised to x also keep as it is. Okay, and now give the denominator as a square plus b square. Okay, give the denominator, a and b it is there now, so give the denominator for a square plus b square. So this one is e raised to x a square plus b square. Okay, I written these two starting steps. Okay, now we have to go for the solving further steps. Now see that it is a sign over here. Now we have sign here, so keep sign positive and the remaining term here cos, which is a you must have to take it negative. Okay, so we write a sine bx, a sine bx. Okay, I consider sign as a positive as we have sign present. Okay, a sine bx. Okay, yes. Next, as we have sign present here, so we consider sign positive. Cos absent, so consider cos, it is the negative. Okay, b cos bx. Okay, yes, how I have written e raised to x upon a square plus b square, a sin bx minus b cos bx here. Okay, so similarly we do here for the next step, e raised to x cos bx dx. Okay, yes, so as we have cos present here, so cos it will be the positive further. Okay, cos it will be the positive, and sine we take it as it is. Okay, yes, so what we write, a cos bx. Okay, we write a cos bx as it is here, as we have cos present, plus b sin bx. Okay, these are the two results important here for our next calculation. Okay, just go through the preparation of this. Some of the integration results are also important. Okay, whenever we change the positions, okay, positions of the integration, then how can we deal? Okay, these are the easy integrations result that I will explain whenever examples are there. Okay, yes, so that is here for our Fourier transformation, basic result for the Fourier transformation. So in our next part, I will explain to you all what is the definition of a Fourier transformation. So let's get start Fourier transformation and its definition. So Fourier transformation, okay, we will define Fourier transformation here. Okay, now see that we have to take some interval. Okay, Fourier transformation we define it for using integral. Okay, so for integral operator we need to know upper limit and lower limit. Okay, so that you learn definite, indefinite integral previously. Okay, yes, so for finding the Fourier transformation, whenever we have now Fourier sine transformation and cosine transformation take some selected interval. Okay, but Fourier transformation can define for entire interval, that means minus infinity to the plus infinity. Okay, so whenever we have any variable x, okay, so if we are going to take Fourier transformation with respect to x, so whenever we have any variable x, okay, any variable x which varies from minus infinity to plus infinity, then we go for finding the Fourier transformation. Okay, now see that when f of x is defined on minus infinity x infinity, okay, so what we have here, f of x defined, where it is defined minus infinity to plus infinity. Okay, that means f of x, this f of x we have here, okay, the x which is coming from that f of x now, which defined from minus infinity to plus infinity. Okay, so that minus infinity to plus infinity, that function defined. So whenever this condition happen, we consider the Fourier transformation. Okay, now see that Fourier transformation, it defined as capital F. Okay, capital F we denoted as a Fourier transformation. Capital F is a Fourier transformation. Capital F is a Fourier transformation. And a small f. Now see that we are not going to learn only the Fourier transformation, we are going to learn inverse Fourier transformation also. So small f we define inverse Fourier transformation. Inverse Fourier transformation. Okay, so capital F is the Fourier transformation, small f it is the inverse Fourier transformation. So these two conditions we will apply in our next examples. Okay, yes. Now for any function, how to find Fourier and inverse Fourier transformation, we are going to understand some important results for this. Okay, now see that capital F I define as a Fourier transformation. Okay, so capital F I define as a Fourier transformation on a variable s. Consider any variable. I consider s as the variable that f Fourier transformation defined here. Okay, and small I define here on x. Okay, small inverse Fourier transformation I define here on x. Okay, so how I have defined, I will explain to you all. Just need to understand the terminology first. Okay. Oh yes. So now see that capital F of s be the Fourier transformation of f of x, and small f of x be the inverse Fourier transformation of capital F of x. Okay, so small f of x and capital F of x, understand the difference between them. Okay, yes. So what we do, we are going to write a formula for Fourier transformation. Okay, so Fourier transformation we write f of x. Okay, we write Fourier transformation as f of x, which is equal to, we know that minus infinity to plus infinity, it Fourier transformation defined on minus infinity to plus infinity, that means entire all values. Okay, yes, small f of x into e raised to isx dx. Okay, into e raised to isx dx. So this one is a formula for finding the Fourier transformation. Okay, see it carefully, it is very much important here. Capital F of x is equal to minus infinity to plus infinity into small f into f of x into e raised to isx dx. Okay, this one is a yes. Okay, isx dx, which is the Fourier transformation. Okay, yes. Now we want the inverse Fourier transformation. That means if we entering to the Fourier transformation, so we have to understand the revert back process. So it defined as the inverse Fourier transformation f of x. Okay, which is 1/2 pi minus infinity to plus infinity capital F of s. That means this one is the capital F, means Fourier transformation of it. Okay, yes, e raised to isx dx. Okay, that is a negative sign here, e raised to minus isx dx. Okay, yes, this one is a ds. So this one is the inverse Fourier transformation, and this one is a Fourier transformation. See guys, these formulas are very much important here. Okay, so I mention here capital F as a Fourier transformation. Okay, yes. So this one is a complete definition for Fourier transformation. You all need to understand. Okay, so behind of these formulas there are some proofs and reasons are also there, but we are not going for this one in our today's lecture. I will explain to you all in another lecture. Okay, so this one is the formula for Fourier transformation, and this one is for inverse Fourier transformation. So get prepared with these formulas. We are going to apply some of the examples. Okay, based on the Fourier and inverse Fourier transformation. Okay, so I hope you all have understood guys my today's lecture. This is only just a basic lecture here, formula and basic, based on the formula and basic results. I hope you all have understood everything here in my today's lecture. So even after, if you found anything confusing, difficult, let me know, guys. Okay, yes. So in our next lecture we go for solving some of the example based on the Fourier transformation. Okay, yes. So that's it here for our today's lecture. So thank you everyone, thank you for my today's lecture.